Am I audible?
नाही.
Okay, now am I audible? Hello?
Yes, ma'am.
Okay, okay, okay. So let us continue with our complex analysis. Here we start with our second chapter, that is elementary functions. I think no issues. Is it going fine? Is it properly audible?
Yes, ma'am.
नाही मॅडम, खूप कमी आवाज येतोय तुमचा.
Is it fine now? Okay, Anjali?
हो मॅडम, थोडस जास्त येतोय आता, पण नेहमी सारखं नाही येत.
Okay, but adjustments are the same. Okay, I would like to continue because we have less time. We will deal with the second chapter, elementary functions of complex analysis. We begin with the exponential function. As you all know, complex number, whenever we say, it is just z equal to x plus iy kind of number, but I itself is imaginary, whereas x and y, the components, they're real. So in other words, sometimes we denote this by ordered pair xy also. So single complex number, it's an ordered pair of two real numbers. So this way we have to deal with a complex number. Now, if I apply the exponential function, does it obey the same rules of real functions of real variables or not? That we want to see. So all of you see here, we start with our exponential function, exponential of z. How do we write it as? E raised to z. But z itself is x plus iy. So by the rules of indices, actually e raised to x plus iy, we have to bifurcate as e raised to x into e raised to iy. And you all know e raised to iy is Euler's function. Euler has given this equation, e raised to iy is nothing but cos y plus I sin y. So this number e raised to z now becomes e raised to x in bracket cos y plus I sin y. Now we are interested in checking whether it obeys the laws of indices as a whole or not, as far as the complex numbers all are concerned. So we take two complex numbers z1 and z2, namely x1 plus iy1 and x2 plus iy2. Now e raised to z1 plus z2, e raised to z1 plus z2 will be equal to e raised to z1 into e raised to z2 as per our laws of indices. We want to show it, it happens. Okay. So we want to show that e raised to z1 plus z2 is nothing but e raised to z1 into e raised to z2. So is it really true? That we want to check. So let us begin with our LHS e raised to z1 plus z2. What I mean by z1 plus z2, real part plus real part is the real part and imaginary part is the sum of the imaginary parts. So we got e raised to x1 plus x2 plus I times y1 plus y2. By Euler's expansion, e raised to x1 plus x2 out as it is. And for this imaginary part, we write as cos of y1 plus y2 plus I sin y1 plus y2. Now, this x1 plus x2 being real, we already know that this particular part I can write using laws of indices. And it becomes e raised to x1 into e raised to x2. Now, inside the bracket, let us try to expand. Now, the real part. What we'll do is cos of y1 plus y2. We will expand as cos y1 into cos y2 minus sin y1 into sin y2. Then plus I times sin y1 cos y2 plus cos y1 sin y2. That we know. Now, what we'll do is out of these terms, the highlighted terms, let us try to find out the common term, that is cos y2 out. So if I take cos y2 out, what I'm left with? Inside I'm left with cos y1 plus I sin y1. You can immediately watch. Now, the not highlighted, unhighlighted terms, let us deal with. That is minus sin y1 sin y2. And this one is I times cos y1 sin y2. I find sin y2 is common term. And because there is minus sign, I can adjust I square with it. So I have adjusted I square sin y1 sin y2 plus I times cos y1 sin y2. From these two terms, I can take sin y2 common with I. So that we have done. Inside we are left with cos y1 plus I sin y1. And you see the bracket as a whole is common bracket. So we will take bracket common and we are left inside with cos y2 plus I sin y2. Only while writing, we have taken care that along with the cos y1 and sin y1, we will have e raised to x1. And along with this cos y2 plus I sin y2, I can write e raised to x2. So that I'll get this to be e raised to z1 into e raised to z2. So we very immediately observe that the rules are followed. This is nothing but the RHS. So we have shown that e raised to z1 plus z2 comes out to be e raised to z1 into e raised to z2. So the same laws that we have seen in real functions are followed by this function also. Now, same way I can prove that e raised to z1 minus z2 happens to be e raised to z1 upon e raised to z2. Now the next important thing is what will happen to e raised to 0. So by this law, what I can do is I can go for e raised to 0. How I'll adjust this 0? I can say e raised to 0 is nothing but e raised to z minus z. Can I? Z minus z I can read as 0. And this by the second law, e raised to z upon e raised to z takes me to 1. So I feel that you have followed the third law also. E raised to 0 happens to be 1. Then I can move to the fourth law. What I'll do is I'll take the help of second and third one and let me write e raised to 0 minus z. Minus z can be written as 0 minus z. So this will happen to be e raised to 0 upon e raised to z, meaning thereby 1 upon e raised to z. So I think you followed all the laws. There was nothing. Actually, this is just a kind of extension to complex plane. I would like to move ahead. Now the very important thing for us is e raised to z is never 0. E raised to z is never 0. So whatever complex number z you take, e raised to z is never 0. As we have seen in case of real numbers, e raised to x is never 0. Same way, e raised to z is never 0. Now let us come back to what is our exponential function. So we have seen here exponential of z we can write as e raised to real part into cos y plus I sin y, which is quite important for us. So the same thing I can write as what? Rho times e raised to I phi, rho times e raised to I phi. So what is this rho? Rho is nothing but the modulus. As we have just now seen, rho will be e raised to x, and phi will be the argument. So phi will be y. To be more specific, we know it depends on cos and sine, and cos and sine both are periodic functions. So they being periodic, they repeat after every 2 pi. The period will be 2n pi, and because we are adding it to the argument, there is I along with it. It is attached with I. So what you observe, the modulus of e raised to z is always rho. How to get this rho? This rho is nothing but e raised to x. And what is this argument? Phi. Argument phi is nothing but y plus 2n pi, and n stands for any integer. N is an integer. So what you observe over here, e raised to z is periodic, and period is 2n pi, sorry, 2 pi I. So in period, I will always appear. Period is 2 pi I. Alright. Now to see the periodicity, I have tried with the GeoGebra Classic. I tried to get its graph. So you can see I have typed here e raised to x plus iy, and range for x is given from minus 10 to plus 10, range for y is given to be minus 10 to plus 10. So what do you observe? This kind of repetition occurs, this kind of circles you go on observing along with. Okay, so it's a kind of surface which is periodic kind of thing which repeats itself again and again. I feel it's okay. Now the very important thing is this property. E raised to z may be negative, which is distinct from real world. For the functions of real variables, you'll never get e raised to x to be negative. But e raised to z goes negative. It goes in both the quadrants. So I would like to just help you. I would like to go with GeoGebra Classic as I have shown here. So what you observe, this kind of circles are produced again and again. So e raised to z is a kind of periodic function. It repeats itself. But now I would like to type e raised to x for some real value, e raised to x. And you can observe the graph is somewhat shown by red. Yeah, this one. So what do you observe? It doesn't cross the x-axis. It is upside. It doesn't cross the x-axis as you are watching. Let me go somewhat nearer to this. So what do you observe? It's a kind of graph which is starting from the first quadrant and going into second quadrant itself. It doesn't cross the x-axis. It is only in the upper half. Whereas if I go with this particular, you can see it is going down also. Is this fact clear to you? Is it okay?
Yes.
Okay. So e raised to z may be negative. So for complex numbers, this is the basic change. Okay. When it will be negative, so you know very certain that cos pi is -1 and sin pi is 0. So e raised to I pi will be cos pi plus I sin pi. So very obviously its value will be -1. So cos pi plus I sin pi is nothing but -1. And because it repeats after every 2 pi I, you can observe that e raised to I times 2n plus 1 pi will always be -1. Is it okay? Now let us move ahead. I think I'm not fast.
No, ma'am.
Okay. Okay. Now, what kind of questions are there? So they might ask you to show this or compute it likewise. And then we have to go to the analyticity of the function and so on, entireness, etc. So first we will show that exponential of 2 plus minus 3 pi I is nothing but minus e square. So what you observe here? Z is equal to 2 plus minus 3 pi I. We find its exponential, means we raise it to the power of e. By laws of indices, it has to be e square into e raised to plus minus. Actually, it was 3 pi I, but because the period is 2 pi I, it comes down to plus minus pi I. And because it is coming to plus minus pi I, it takes us to cos pi plus I sin pi or minus I sin pi. So both ways, sin being 0, you ought to get only the value of cos pi, which is -1. So you are getting this to be minus e square. Is it fine?
मॅम कॅन यू प्लीज रिपीट दिस म्हणजे ते वरती कसं आलं ते नाही समजलं.
कोणतं?
प्लस पाय आय पाय
Okay. Actually, it repeats after every 2 pi I, as I said. 3 pi I minus, yes, pardon? Uh, I couldn't listen to your question still. I feel you are dealing with plus sign ones, minus sign ones. Is it so? Is that so?
No, ma'am, understood.
Yeah.
Means after 2 pi.
Yeah. The thing repeats after every 2 pi I. So we are dealing with it and we are trying to take the principal values, isn't it? We are trying to take the principal values. That's the thing only. What are the principal values? Come on. What is the range of theta? I think I have shown it to you in Argand plane. How the theta lies between what to what? Priya, Gauri, Suvarna? Anjali?
Minus pi to pi.
Yes, that is it. It varies from minus pi to plus pi, we know. And that is why we have tried to stick to this particular value. Is it okay?
Yes, madam.
Okay. So that way we have shown that exponential of z is minus of e square. Alright. Now I would like to go back to okay. So this question, show that exponential of 2 plus pi I upon 4 happens to be root e by 2 times 1 plus I. Can you do this? Yes, come on. 2 plus pi I upon 4. Come on, what this will be then? It will be e raised to, I would like to directly go with 2 by 4, meaning half. In the bracket, what I'll get? Cos of pi by 4
By 4
plus I sine pi by 4. So it is so easy. There was nothing. What is the value of sine pi by 4 and cos pi by 4? Yes. 1 by root 2. Yes, it is 1 by root 2. And this e raised to half, can I write as root e? So what I have is 1 by root 2 plus I times 1 by root 2. So this root 2 is common. So I can take this root 2 out and this becomes root of e by 2. And in the bracket I'll be having 1 plus I, there is nothing. So I think this kind of questions are quite easy. Hope you agree. Then I would like to go next to the next question. Exponential of z plus pi I is equal to minus exponential of z. I repeat the question. Exponential of z plus pi I is equal to minus exponential of z. Exponential of z plus pi I. So what this means? Either you start with z as x plus iy and then continue, or otherwise you treat z as one complex number, pi I as second complex number and continue. So I think I would like to go like z plus pi I in the index. I hope you agree. And we have seen the laws of indices. So what this gives me? E raised to z multiplied by e raised to pi I. Can I say so? Come on.
Yes.
We have seen here e raised to z1 plus z2 is nothing but e raised to z1 multiplied by e raised to z2. That is what I have done over there. So we reached over here z as our first complex number, pi I as the second complex number. We can split so. Now what will happen? This will be equal to, I can't do anything until I know what is z. So e raised to z has to remain. And as far as e raised to pi I is concerned, you know better that it is cos pi plus I sin pi. And sin pi being 0, it has no contribution. And cos pi being minus 1, the sign will be simply minus e raised to z. Do you agree? This value is 1 plus 0i. So it is, sorry, minus 1 plus 0i. So it is minus 1 only. Hope so. I would like to, yes, plus 0i. Is this fine now?
Yes, ma'am.
Okay. So now again I would like to go back to the exercises, and the question is, state why the function f of z equal to 2z square minus 3 minus z times e raised to z plus e raised to minus z is entire. Can you solve this question? I would like to highlight the function so that you can read it easily. Yes, can you solve it? Two z square minus 3 2z square minus 3 minus z e raised to z. I would like to once check whether it is plus or minus. Okay, minus z e raised to z plus e raised to minus z. You want to show that it is entire. What do you mean by entire function? What is entire function? Huh? Come on. What do you mean by entire? You're not audible.
Everywhere.
Yes, it is differentiable everywhere.
Yes, it is analytic everywhere.
Yes, it is analytic everywhere. And analytic everywhere itself means it is differentiable everywhere. Everywhere, if I say, it means that it is differentiable everywhere in the neighborhood of each point. And that is why it is entire. Is it okay? So by entire, I mean that it is analytic at every point and it is differentiable at every point. Got it? Uda? Okay. Now, I want to show that this function is differentiable everywhere. So very first, what are the requirements for us? At any general point z, we will try to show that function is differentiable at any z. Okay. So we have to go with ux, uy and all that. So can you go for this? So you may say f1 of z is twice z square. F2 of z is z into e raised to z. And f3 of z as e raised to minus z. This will work. You have three different functions. Okay. Go with your sufficient conditions for differentiability. I think you are capable to show that each of these is an entire function. And then you will say that the sum of two entire functions is to be entire. Okay. Sum of three functions is to be entire. So all sum of all those functions becomes entire, and that is why f becomes entire. Would you work for this? What you need to do is go for sufficient conditions. What are the sufficient conditions? Come on. Gauri?
Partial derivatives
Yes.
exist as a
Yes.
continuous function.
Yes, all the
And
partial
the
derivatives
equation
exist are
satisfied.
continuous. Cauchy-Riemann equations hold. So if yes, so if this happens, we say that function is differentiable at that point, and we are not fixing our z. This is any z, any complex number. So we get the result for every point in the complex plane. Got it? So I feel solve it and show it back to me. Okay? And I would like to move for the further exercise. We have very less time with us now. I would like to go with the exercise. The question says, use Cauchy-Riemann equations and show that the function exponential of z bar is not analytic anywhere. So already we have done this. Exponential of z bar. Already we have done it. Is not analytic anywhere. So how do you write it? You write it as e raised to x minus iy. Is it sure? So this is nothing but e raised to x cos y minus I sin y. And you will show that the Cauchy-Riemann equations fail here. Actually, the function is differentiable. I'm sorry. The partial derivatives exist everywhere and are continuous even. But the Cauchy-Riemann equations do not hold. So let us go with that. What is your u? E raised to x cos y. V is minus e raised to x sin y. Just differentiate it and see what do you get in hand. What is ux? E raised to x cos y. What is uy? Minus e raised to x sin y. What is vx? Minus e raised to x cos y. And vy is minus e raised to x cos y. Is there any mistake? I think there is a mistake. This must be sin, isn't it?
Yes, ma'am. Vx is minus e raised to x sin x.
Yes, it must be sin. I'm sorry. Okay. So what you observe? Ux and Vy, they must be equal, but they are not. They are negatives of each other as you are watching. You want these two to be same, but they are not. They are negatives of each other. And if you go ahead with the next one, Uy, this one, and Vx, you want them to be negatives of each other, whereas they are equal. So the function is not analytic. Did you get my point? Cauchy-Riemann equations do not hold. What is your requirement? Your requirement is ux must be equal to vy. Whereas you are getting ux is equal to minus of vy. And uy is equal to minus vx. Here you are getting both are equal. Okay. So Cauchy-Riemann equations do not hold. Okay. CR equations fail. And because CR equations fail, the function cannot be differentiable. Got the point?
हो मॅडम.
Okay. So third question is also over. It is not analytic anywhere. It is not analytic anywhere. Okay. Fourth question says, show in two ways that the function f of z equal to exponential of z square is entire. So let us forget about these two ways. At least once we should be able to. So how would we go? Exponential of z square we want to go. And we want to show that it is an entire function. So just now, whatever we did, we found out the partial derivatives, we tried for the Cauchy-Riemann equations. You go that way and see whether it is differentiable everywhere. Differentiable everywhere in the complex plane itself means it is analytic everywhere, and that means it is entire function. Okay? So your target is to show that it is differentiable at each and every point in the complex plane for any z. So let us deal only with these 4 questions. I hope you are taking screenshot of this particular. Please take screenshot of this. Over.
Yes.
Hope ready. Ready all?
Oh, madam.
Okay. Okay. Now see, I will be sharing this video to you. And these questions we have already solved over here. If there is any doubt, then we will try to solve it in the next lecture. Is it okay? Maybe online or maybe offline. We will deal with it. But I think it was successful. Okay.